Да?
Егор,
Да.
только просьба перейти на английский. Let's switch to English.
Хорошо, окей. English. Tough language.
Or Italian.
Possiamo parlare italiano? Anche in italiano, sì.
Кто-то пришел, да?
Okay, so let's start. So today I'm going to try to present some story about brains and how they cross. So this is part of some ongoing investigations in the relation between quantum toroidal algebras or dim algebras and string theory. So we started all with this refined topological strings, but then it turned out that the theory is somewhat richer, so that there are lots of that it actually describes a zoo of brains, a zoo of representations of the algebra corresponding to brains. So let me start with the general idea, like the dictionary, which I'm going to promote. So the idea is that there is an algebra which I may call a brain algebra or BPS algebra, and its representation. So, well, we will move gradually. So first of all, the representations of this algebra. So in our case, we are going to consider a particular example. This is this Ding Johara Miki or quantum toroidal. There are lots of names, and many people approached this subject in different ways and invented different names for this algebra. And also there are many notations, of course. So this is sort of a double loop algebra, a quantum deformation of a double loop algebra. And the idea is that this is what we can call a brain or BPS algebra of to be strings. So that's the idea. In a particular background, of course. So there are parameters. These parameters will correspond to the parameters of the background. And so what does it mean? In more practical terms, that the representations of this algebra correspond to bound states, sort of bound states between PQ strings and different brains of type 2B. So in type 2B there is an SL2Z symmetry, S-duality symmetry. So there are PQ strings. 1, 0 is the fundamental string, which is also denoted by F1, and 0, 1 is the D1. D1 brain. So the SL2Z transformations, they rotate, naturally rotate these PQ numbers. And then there is so there are of course more brains in this story, more objects. So everything starts with D-1, so this we are not going to consider. I may comment in the end on the role of D-1. They are sort of implicit, so in the construction they are summed over. So this I'm not going to enter explicitly. But then there are in order of increasing dimension, there are D3 brains, right? So the D3 brains, they're result-to-Z invariant. And then there are PQ5 brains. So let me list them like this. So this one. So this I'm going to put in bracket because it will be implicit and 5 branes.
So D3 doesn't mean that it's 0.3.
No. So D3 is a cell-to-Z invariant. So on the world volume of D3, leaves n equal 4 the world volume is 4-dimensional. So there leaves n equal 4 young means that there is a stack of them. If there is one it's U1. If there is a stack, then there is UN, which is exactly a cell-to-Z invariant, exactly S invariant. So this S invariance or SL2Z invariance, it stems from the SL2Z invariance of the string theory. So
you are describing
a set of branes, and then I'm going to, in the left-hand side, I'm going to put the corresponding entries in the dictionary representations. So here are going to be representations.
So Igor, when you say PQ strings, these are all strings that is one-dimensional. Yeah?
The strings
PQ
are...
string. What is PQ string when P is 5 and Q is 7?
It's about state of 5 of this and 7 of this.
I see. So whenever you have this PQ, you're just adding the charges of these letters of the strings, if you wish. I see. And then all other branes, the claim is that these are certain representation of SL2Z or...
Yeah. No, the SL2Z acts on them, acts between them. So SL2Z will transform some representations into other representations, while others will be invariant.
So SL2Z, which acts on the representations of this Dinka-Hara,
yes.
It acts somehow...
Yeah, it acts on the algebra. It's an automorphic group of the algebra. So some representations are invariant, while others transform into each other. So there are like orbits of this SL2Z. So there are this PQ5 branes, and then the story gets murkier and murkier when there are 7 branes. And to this I'm not going to, well, there will be something tentative on the left-hand side, but I'm not good. So these also have PQ charge, PQ7 branes, but for this I'm not. This I'm not going to pursue in detail. So mostly I will talk about this only 3 sorts of branes, which is still not such a small dictionary.
So in the 2 last we have some numbers like 7 or 5 per branes.
Yes.
Anything that in first have 1 brane, means it is the same as 1.
Yes, absolutely.
And D3 means you have 3 branes.
Absolutely. So this thing is 4-dimensional. This thing is 2-dimensional. So the dimension is always 1 plus the number here, because.
And for D3 you don't have PQ parameter.
Yes, it is one. It's sort of unique.
So it's a wrong impression, or what is wrong? So if you have PQ strings, then Q corresponds to sort of D string charge, yes?
Absolutely.
But for other branes, that's not true.
For other branes, it is also true.
But there are no fundamental objects like fundamental strings, yeah?
So here, let me explain it here. It is, so 1, 0 in this case is a D5 brane, while 0, 1 is an S5. So
in the same normalization, like
yes. So
like the charges change. Why? So what is?
So there is so PQ string can end on a PQ brane. So if one can end on D5, so that's the rule. Yeah, I had a lot of confusion with these notations, which one is PQ and which is QP. So, but I think I consulted with.
Is there any strict definition of these charges? An operator which in string theory that you can.
So for D5 we have the Ramon charge, the corresponding Ramon charge, and for.
Well, I mean universal, that it will give simultaneously 1, 0 for or 0, 1 for D1s and 1, 0 for D5.
Okay, so I'm not sure. So I think there is. So in that case, there is again. So all d charges they correspond to Ramon charges. There are corresponding Ramon forms, and you integrate them over around the brane, and then you have the charge. With F1 and S5, you integrate the B field and the dual of the B field. So that I'm not sure I'm going to give a universal definition. I'm not sure. It may exist, but I don't know. So yeah, unfortunately, my understanding of string theory is rudimentary. But anyway, so the claim is that there are representations corresponding to this to the right-hand side. What are they? So if so, some people here are familiar with the representation theory of this algebra, and there are different sorts of representations. There are so-called vector representations.
Егор, excuse me. Are you going to define this Q1, Q2, Q3 double algebra? Or?
Yes, let me. I wanted to make first an announcement of the dictionary so that it will be the motivation will be clearer, and then start with technicalities like defining the algebra and I'm probably going to write out the generators and the relations of the algebra. But first, I wanted to motivate this by writing out this dictionary. So, unless you absolutely insist, I would first write this as a motivation. So the representations are of several types. There are so-called V, the vector representations. And these are going to correspond to this difference. So, what are these? How do they look? There are representations on functions. There are the algebra acts on functions, and it acts with the multiplication by polynomials in W, say powers of W, and also by shifts of W. So there are operators, difference operators in W. So there are these types of operators which act on functions of a single complex variable W. And so this Qi, which so what does this operator do? So it shifts W into Qi power m W. And I goes from 1 to 3. So there are these three parameters in the algebra, and for each Qi there is a different representation. There are three representations. I with I 1 to 3. So we will see how it corresponds to this brane picture, because in our background there will be three types of different branes. So this there are this vector representation, and we will also see maybe then what is the role of these shift operators. So how do they act in the different brane picture? So there are the fork representations, F. There are representations on the free chiral boson Fock space. So there are states like A minus and 1, etc., A minus and K acting on the vacuum with some momentum, denoted by U. Let us put this U here. But also there is a wealth of these representations parameterized by two integers P and Q. So these representations are going to correspond to these 5 branes. And then there is one more level here, which is called the Makumakano representation, where the states are parameterized by 3D Young diagrams. And there are several of them also. So they have, in principle, they also have this PQ here. So the states are parameterized by 3D Young diagram, or also called plane partitions. So this has something to do with the 7 brains, but this is not completely clear. So what is the role of this guy? So let me say that so this PQ string.
You're saying that that representation do not have PQ parameter.
So this one doesn't. This one doesn't. It's invariant. It's invariant.
And I disagree.
Okay.
And for first, you explain what is not strings.
Yes. Yes. So the strings are. The strings correspond to the algebra itself, the generators of the algebra itself. So the PQ string would correspond to, well, roughly to a generator. How do I call it? Let me call the generator E. Okay, P, large EPQ. So these representations are. So this is start here. So there is this generators of the algebra. We'll see more precisely what does it mean. So how a string corresponds to a generator. Well, that's not exactly not the exact statement. The exact statement is that the junction of a string with a brain corresponds to inserting a generator, the corresponding generator, and acting with it on the corresponding representation. So hopefully we will see it. So let me now, after this announcement, I make...
But what does this? I want to ask you. So the action of the generators of algebra is more or less a string ending on a particular brain. Yes. So if it is an operator of an algebra, it does something with the vectors of this representation.
Yes.
And what does it mean in terms of brains? So you have to compare brain with the junction with brain without junction, or what?
We'll see in the background that there will be a distinguished direction. So the brain will be sort of conjunctified, or some directions of it will be subject to omega background, but there will be one dimension which is left. And this dimension will be the quantum mechanical time direction in which the operators are ordered, and there is a well-defined ordering of operators which act sequentially. So the junctions will be ordered in one of the directions in the background. And this will correspond to ordering of the operators. So let me do one more thing. Let me draw.
I asked actually a simpler question, but there is a single operator. Huh? So, and then it's somehow located in this direction. So, but what it does with the brain?
For example, if you have a defined brain and you add a junction with the D1 brain, so that's not exactly what is happening, but you can think of it as that you add an instant one. So you add an instant, the instant number changes by 1 if you add a D1 brain. So there can be a bound state of D1 and D5, of several D1s and D5. So if you start with some number k of D1s bound to D5, this corresponds to instant number k. And then you add one more. So that's what it does to the brain. So it changes the state.
It changes the quantum numbers of the states.
Yes. Yes. Okay, so let me draw the background in which this right-hand side will live, because it's not a universal thing. It's not that I imagine whatever background I can imagine, and then there is a correspondence. Well, I don't claim this, and this probably isn't true. But there is a particular background where this left-hand side picture seems to work. So, how do I do this? Okay, I hope it's visible here. So I have three complex directions in which I have an omega background.
You can ask people on the chat, the Zoom, do they see, correct? Maybe you should write large.
Okay, so should I write larger? Should I skip this lower blackboard, or is there a problem with this?
Is anyone alive in the
I guess it's fine if they don't answer.
in Zoom?
Everything goes smoothly, everybody is asleep.
Yes. Could you say it again?
You just don't hear them.
No, I think we hear.
So let's, well, I will try to continue, and if there are objections, then I will try to somehow adapt. So there are this is a six-dimensional part. So in total, I need 10 dimensions, right? It's string theory. So I have 6 dimensions like this, where Q1, Q2, Q3 are this omega background parameters. So I have also, so there are 4 dimensions left, right? So I have, I draw them like this. I have the coordinates x, y, and
You should probably remind that type 2b string is 10-dimensional theory.
yes, type 2b string is a 10-dimensional theory, right? So absolutely, and the background looks like this. I have a circle, a compact circle, and I have three dimensions in which I'm going to draw some pictures corresponding to branes.
So what is third letter? R, X, Y,
And tau, so
so this is time. Or
this is time, but I cannot use t because t is usually Q2. So that's the problem. I actually use it in the paper, and that's my mistake. So we have
so in space-time is R3 cross S1. Yeah.
Yeah,
And
more or
S1 is space dimensional. More or less.
yes. So most of the pictures I'm going to draw in this XY plane. So let me now write where the branes are located. So which directions the branes span. So I have, for example, I have I have F1, which is 2-dimensional. So it's going to be point-like in this direction. So because of the omega background, the things should be invariant under rotations of this C plane. So they either span the whole plane here or sit at the origin. So there are 2 possibilities only. And here, so there are two dimensions which I have. So the one is going to wrap this S1, and the other is going to be here, if I remember correctly. So that's this. I'm going, and on the right hand side, I'm going to draw it in the XY plane. So here is Y, here is X. So F1 I'm going to draw by using a wavy line. So this is the F1 string. And it sits at a particular value of tau. So
it's your choice or what?
Yeah, currently it's my choice, but eventually
in principle, from what you said, it can be totally put to this one of these complex spaces.
Yes.
But then it would be some sort of infinite string. So
yes.
Which is probably not. Also, I don't understand. So, what means that it does not touch time direction? So it's kind of.
It's at a fixed time.
At fixed time, just.
So if you have something happening in time direction, then at some point there is a stroke of a lightning, and that corresponds to an operator of joining the string. Currently that's my choice, but eventually the whole picture should be. I would like to. I'm not an expert on this, unfortunately, but the supersymmetry needs to be preserved. Some amount of supersymmetry needs to be preserved. I'm not going to talk about how many and how, but that's from some classic papers where people studied this PQ brain webs and stuff. So they determined that to have some supersymmetry left, one needs to put branes in particular directions corresponding to their PQ charges. So in particular, this XY plane will correspond to, so the orientation of a PQ brane or PQ string, the slope of it should correspond to its charge, its PQ charge. So it's tied with this PQ charge. And this automatically guarantees some nice properties like supersymmetry. So for D1, therefore, it's also points like in these directions and sits at the origin, but here it's different. So it also spans S1, okay? But here it spans X. So I have here this D1. So of course now I'm drawing it as a segment, but eventually, if I want to make a picture with finite energy, I'll have to introduce some branes on which the strings end. So there can be some branes sitting here, on which in between which the fundamental string, for example, can be stretched. D branes. So our next.
Простите, это продолжение словаря, да?
Да. Yes.
То есть потом будет определение.
So there is a physical part, there is an algebraic part. In the algebraic part, there will be definitions, and the physical part, there is only some head waving nonsense. So that's the idea. And there is this D3. Yeah. The D3. Now we have 4 dimensions to put somewhere. So we still, this is more or less determined by supersymmetry. So D3 should be orthogonal. It should sit somewhere. So it sits at a point here, but I don't have an omega background in this plane. So this point can be somewhere. This can actually sit somewhere, and we will talk a little bit more that, a little bit more refined picture is that this brane is actually delocalized. So this X and Y coordinates of this brane don't commute, and okay, let's not touch it. Currently we will probably return to it in the future. So D3, by the way, how much time do I have? So what are the regulations?
Well, normally we have up to hour and a half.
Okay, fine.
So
fine.
Half an hour spent here.
Okay, good. I should speed up. So D3, there are three types of D3s. So it turns out that supersymmetry can be preserved if it spans either CQ1, CQ2, or CQ3. So there are 3 types, and I will put here an index. So this index will correspond here to the index of the representation. So I will have actually different types of D3s. So this is D3Q1, and since my time is limited, I'm not going to draw the others. It's obvious that there is another which spans here, this plane, and that plane. Then there are, of course, D5s and then S5s, and all their PQ bound states. So the D5s, again, everything is going to wrap this S1. And for D5, it spans a pair of this, so it's 6-dimensional object. And here, so let me now attention. So it is like this. So F1 is 1 0 string, and D5 is 1 0 5 break. But they are orthogonal in the XY plane. So let me draw here. Here is going to be this D5. For example, F1 can end.
So this is your argument. You told me before, yeah, that F1 can end on D5. That's why they should be orthogonal.
Yeah, yeah. So in principle, this is part of the supersymmetry argument that the PQ brain can the PQ string can end on a PQ brain only, and the tension should be conserved, so they should be perpendicular. So that's the idea.
Why don't we have D5 Q1, D5 Q2, and D5 Q3?
That's the next thing I'm going to say is this one is Q1, Q2 because it spans Q1 and Q2. Mm-hmm. And there are, of course, two more of them. There are two more types of D5s. So here I should also ensure that, okay, well, that's the next thing. Okay. So there are NS5s.
And they all have charge 1 0, yeah?
So this one is 1 0, yeah, they all have 1 0 charge.
Because they're D5. Yeah?
Yes, but geometrically they lie in different planes.
Mm-hmm.
And then NS5 the same story, so it's now 0 1, and here is situated like this. Okay, fine. Okay, let me try to continue upstairs. So this old stuff I moved down. So what is left are 7 branes. So PQ7 branes. Apparently they should span. So they're 8 dimensional. So they span all of these CQs. So in the sense they are invariant under the exchange of Q1, Q2, Q3.
So there is just one.
In this sense, yes, but there are PQ charges, and that's a bit more tricky. So you see, so this thing is 8 dimensional. So there are only 2 codimensions. So if you look at the, okay, let me draw it here. So there is this one, and there is it's a point here. So in this XY plane, it's a point, and so there are no. That's the totality of codimensions. So in XY plane, okay. Now I can't draw anything. So this is 7 brane. And what are the PQ charges? The PQ charges are actually the monodromy. So there is a monodromy of the coupling constant actually around this the string theory coupling constant around when I go around this brane, and this monodromy is valued in SL to Z. So it is parameterized by a matrix from SL to Z.
So now it's hidden. Your 7 brane is hidden in the table, so it spreads all the dimensions. And in turn, I see.
Yeah. Yes. But this one I'm not going to pursue. So like, please don't ask me some nitpicking questions about 7 branes because that's sort of an not completely understood piece of the story. So,
Can I ask you?
yes.
Why don't you spec it to density brane? Why don't you have one of them?
Well, because there are more dimensions, more codimensions. There are these codimensions. So here is just a point, and all the rest of the string theory dimensions they are filled completely with this brane. So you cannot escape this plane in any way, so that you don't go around. There is a well-defined monodromy. In this case, to get a monodromy, you need a 4 sphere, right? Okay. Anyway, you need a higher dimension contour. Okay. Okay. So this is the physical like head waving nonsense as I announced. But then there are these representations, and these representations they have definitions. So let me start with I will try with the definition of the algebra. I'm not sure it's very helpful, but I want to put it so that.
I'm sorry, may I ask a question? Have you finished with the introduction?
Yes, sorry.
Could you please summarize just briefly? So what kind of algebraic structure you would need from the representation? So what kind of algebraic structure you are interested in?
So the idea is that there is a. So the small statement is that branes correspond to representations, but then the interesting statement is that the junctions of branes correspond to the intertwining operators between representations.
Yes, but what kind of correspondence do you mean? So what would you like to understand on the algebraic part? So what kind of structure? So you have those representations, you have...
I will have relations between intertwining operators. I will have relations from the geometry and from physics of the branes. There will be some relations between intertwining operators and R-matrices. So that's the idea. Okay, so...
Егor, so also about this introduction, so is there any statement that all representations of this algebra corresponds to some branes, or because if not, how these representations are distinguished on algebraic side?
I wouldn't claim this, but well, in reality I don't know, and it's kind of for now it's kind of an occasional finding that you like you write whatever you can write with representations and on the algebraic level, and then you find that it corresponds to some brane picture and to some results which are known in the string theory. Some now they are visible on the algebraic level. So what? Okay. So what is the? Let me have one more paragraph of the introduction. What is the benefit of this strange algebraic dictionary language? When people draw, usually when people draw this geometric picture, there's PQ branes and there's simple pictures in the XY plane. Well, at least that's how they used to draw. They have what you can extract from it. Well, you can extract some very basic things. You know what are the states. You can say that, like, you can draw some classic picture like with two branes and a string, and then you say that this string corresponds to a W boson or something like that in the gauge theory. But that's mostly words. So there are, well, you can get the masses of these PPS states corresponding to strings, that they are proportional to the distance between these branes. And then you learn that you have the Higgs effect and this stuff, but still this is very much qualitative things. So this algebraic stuff, it puts these words into very quantitative things. So if you redraw these pictures and interpret them as intertwiners, after you evaluate these intertwiners between a particular, like in the on the highest weight states, highest weight vectors, you get partition functions. You get partition functions, and you can evaluate them. And then those partition functions, you can have identities on them. You can have recursion relations stemming from this action of the algebra. And these are recursion relations on the partition functions. So now you are talking about the gauge theory, the supersymmetric gauge theory partition function, like Nekrasov function, and its generalizations, like lots of generalizations. But still, on the one hand, it's still geometric, so it's very much in the same sense of like just drawing whatever you can draw consistent with supersymmetry. But on the other hand, it gives non-trivial statements about about quantum field theory partition functions, for example. Okay, so it gives some flash to these brain pictures which people usually draw.
But just maybe the last question on the level of this picture, were these relations known on algebraic side? It's like about Higgs effect, because it was known, 100 years before these brains. But this picture you draw is just a very nice geometric picture for this Higgs effect, where mass is proportional to the length.
Yes.
Is it the same, or here is more that this picture suggests some new relations on algebraic side?
It does. So let me know, because maybe I won't have time to write it explicitly. But for example, there is this brain creation effect, this Hanani-Witten brain creation effect. If you have a for example, D5 brain and NS5 brain, in this picture they are orthogonal, and if they pass through each other in this, so they're separated. Suppose they're separated in tau direction, and then they pass through each other. Well, Hanani-Witten, they tell us from some string theory arguments that a D3 brain is created. A single D3 brain is created between them. So this turns out to be valid at the level of the interference of the algebra. So you can draw the brains, and this is, well, to my knowledge, it's completely non-trivial. So in the algebra, it's not easy to guess, and it turns out to be correct, but I don't know how to derive it abstractly. Okay, so let me start drawing. Let me start with the definitions. The definitions of the algebra, so that it's more understandable. There are many ways of defining this algebra. But there are the generating currents. This is one way of defining the algebra. There are several generating currents. 4 in this case. And there are relations. So the algebra is Z2 graded. So this Z2 is the Z2 PQ charge, the lattice of PQ charges, actually, of the string states. So I can draw. So these are generators of definite grading, and I will draw them in this Z lattice so that it's easier to understand which one is which without writing the gradings explicitly. So this is the picture. So here are psi plus n, here are psi minus n, and here are x plus and x minus. And what do I mean by this? So this is x plus 0, this is x plus 1, x plus 2, etc. X minus 2, x minus 1, x minus 0, etc.
In psi plus, here it starts from greater or equal to 0.
Yeah. Okay. So the ones corresponding to 0, they're central. So they're special. Yeah. Oh well. Okay. The important thing is their ratio, because their product can be scaled away. So it doesn't affect the algebra. Well, both of them are central, but the product is sort of trivial. And then there are relations. The relations are like this. Let me try to write them in a reasonable amount of time. So for this I need to write quicker than I usually write. Or maybe I stop at some intermediate steps and just assure you that there are relations. Where G is a function, G g of x is a ratio of two other functions, and g plus minus is the following third degree polynomial. So they're manifestly invariant under permutation of Q1, Q2, Q3, and this gamma is another central element. So gamma and psi 0 plus minus are central. And these central elements will correspond to, actually correspond to PQ charges of the 5 branes. So, what else? Well, there are lots of relations. I don't know. And all of them contain this either G large or G small. Sorry. I don't know how to deal with this. And they're all of this type. Only two left. And the final one. Plus there are, okay, not the final one, but plus Serre relations. Relations. And this I'm not going to write out. So this I have exhausted my forces. So this is the definition of Q1, Q2, Q3. And what are the properties, the important properties of this algebra? That first of all, Q1, Q2, Q3, one can permute in any way. So on this act, in other words, so the algebra only depends on symmetric combinations of Q1, Q2, and Q3.
Sorry, but where is this Q's in the relations, or?
They are in the G, which is in the G small, and G small is everywhere. So, okay, let me introduce one more thing. So I write the ratio of this two central charges. As I told you, the product of them is irrelevant, but the ratio is important. So I introduce gamma orthogonal. So there is gamma and there is gamma orthogonal, and this gamma orthogonal. This is going to be important pair of central charges. So these are this will correspond to the charge of some branes. So this is a non-trivial statement. There is an SL.
Егор, so we met already Q1, Q2, and Q3 on the left-hand side,
yes.
And where is gamma and this size?
Right. So this gamma orthogonal will correspond to if you have an if you have a PQ5 brane with indices say Q1 and Q2, Then to it will correspond a Fock representation, PQ, Q1, Q2, as promised, but this will have central charges, gamma, gamma orthogonal, equal to, okay, Q3, Q3 to the power P over 4, if I remember, so okay, fine. I can have some factors here. You see, so Q3 is the one which is not Q1 and Q2, right? Oh, okay, sorry. I'm sorry. So Q1 and Q2, the Q2, Q3 are not independent. So this algebra is only defined for these values. And here Q3 you can view as Q1, Q2 inverse. Anyway, you see, so this gamma and gamma orthogonal, they are determined by P and Q. So these are essentially the PQ charge of the 5 brane.
Oh, does PQ only correspond to gamma gamma orthogonal or some other part?
Well, the whole implementation depends on the value of P and Q, but in particular the central charges depend.
And what means that for D3 brane there are no PQ charges? What it means in terms of gamma and gamma orthogonal?
Gamma and gamma orthogonal are equal to 1. So for D3,
on action on functions, this, as you said, yes, so it has no central charges.
yes. So D3 Qi correspond to this VQI, and here gamma gamma orthogonal is 1, 1. So it's multiplicative central charge, so the trivial ones correspond to 1. You can see here. So the degenerate values of these Q's is when, for example, Q3 goes to 1. So that's the sort of degenerate limit of the algebra in which it simplifies greatly. But we're not going to talk much about it. Then there are these representations. So I'm not going to write the relations for representations. That's beyond me. So what I'm going to do instead is to draw some pictures and write some corresponding intertwiners, interesting intertwiners. Okay, there is in this sense, there is a sort of an older story about which I have already told some time ago, and there is a newer part of the story. The newer part of the story that is about brane crossing. And the older part is about some brane junctions. So there are. So let me first introduce some brane junctions briefly, and then I will go to this newer stuff. So brane junctions. For example, I have 5 branes. Imagine I have 5 branes like this, and I can have a junction. So there is. So this one is a D5. This is an NS5. And this is 1, 1. So I can have a junction. What does it mean in the level of an algebra? So I have this Fock representations, and there is this intertwining operator, which acts from the tensor product of two of. So there is F10 tensor F01, and there is an operator, intertwining operator going to F11. And all of them, so geometrically, if you look at this, you have a junction of here of some 5 branes. And how can they join? If they can only join if they share, for example, Q1 and Q2 directions. If they, for example, if I have a brane like this, so it's impossible to join them here in this direction because they just cannot merge these directions. If you think about it, you see that in lower dimensional examples, that's also true. You cannot merge stuff which doesn't share all the directions except this one in the picture. So in these junctions, all of this, they have indices, well, the same indices. For example, Q1 and Q2. So here this is also valid for the representations. And you can draw a whole PQ web like this. There will be a combination of intertwiners, like I can draw the arrows to emphasize where the operators act, and I can combine these operators in a in a complicated way. So this one is going to be I also need a dual intertwiner which goes in another way. I have more data actually. I have spectral parameters like U and V. This U and V, they correspond to positions. So this D brane, for example, it spans Rx, but here in Ry, it sits at a different position. And this location is encoded in the spectral parameter of it, like U. U is like exponent of this position. Position in this direction, and V is the position in this direction. So I will have, for example, U, V, and then there will be, I don't know, V prime and U prime. There will be some relation of them because the picture should match. But the important point is that all this happens for Q1, Q2 branes, 5 branes. This is the PQ, the classic picture of PQ5 brane web. What I can do with this web, I have a combination of intertwiners. I can evaluate them on the highest weight states. So this is the picture of which was put forward in the paper of Avate, Fagin, and Shiraishi. I don't know, I guess in 2012, I think. So I can put here the highest weight state in the Fock space. This is the vacuum state. And evaluate these operators acting on this. And this is going to be the partition function of a theory living on the 5 brane web. And this we know very well that one can draw webs and one can extract gauge theory results from this. This is going to be Nekrasov function. And as you know, in Nekrasov function there are 2 parameters, equivalent parameters. There's a 5D gauge theory, Q1 and Q2, and there are also this U, V, U prime, V prime, which will correspond to some moduli of the theory. Okay, so this is sort of an older stuff.
And P and Q, what is in Nekrasov?
Well, if you have a choice, sometimes you don't have a choice because you have to balance the tensions everywhere. You have to conserve PQ charges. But when you have a choice, it's Chern-Symons, the value of Chern-Symons coupling. So you can have different values of Chern-Symons coupling sometimes.
Use 5 dimensions.
It's 5 dimensions.
Of course, it's 5 dimensions. Okay. That's, yeah, of course, these are dimensions, but from 2 P and Q, for example, here 1, 0, 0, 1, 1, 1. Well, naturally would be suggested that there is no Chern-Symons term, yeah?
Well, here in this simplified example, there is no choice really because everything is fixed. If I have this external states, then I cannot do anything. Everything which I can obtain from this picture by SL to Z action, that's equivalent. Z will be SL to Z invariant, so there will be no choice. But sometimes I do have some choice, like if I have a more complicated picture. Well, it depends on how you modify it.
I mean, you have a restriction that this line do not intersect R.
Yeah.
But I thought there are 2 choices.
That's possible. I don't claim
this. This is U1 theory. For U1 theory, for UN theory, which you're saying.
Wait. But for this, I need something like this, right?
No, this is U2 theory. But yes, this is okay. I mean, you can draw the. Now your parallel lines is some sort of.
То есть это вообще не калибровочная теория, да?
You can draw the picture when the parallel lines are first and second.
Maybe I can. Maybe you're right. Because I can have. Right, maybe I can have here not just something like 0, 1, but 0, 2, or something like that. That would be more complicated.
I think there are two pictures in this case. And this Q1 theory turns out up to 1.
Yeah, probably you're right. Probably you're right. Yeah, I remember that there are like, it's 0, pi, or something like this. There are two choices. So,
but just Igor, to avoid, since I had a confusion, so this picture is not a picture for a gauge theory, yeah? This picture, which is just on the blackboard.
the picture for, well, this one is a picture for something like a free multiplet.
Yes,
like
free multiplet, and gauge theory appears like the first maybe non-trivial cases, this long picture.
Yeah, absolutely. I just drew this so that it's simpler. Okay, one can have a junction between five branes and three branes. So that's another option. In this case, the partition function will be a, how do I draw this? Okay, so there's 5 branes plus the 3 branes. So this can also join together, and this will be a coupled system of. So this 5 branes correspond to a 5D theory living on the world volume of the web. So five branes are actually the 6-dimensional, but then there are finite segments here. So one dimension is the dimension is finite. Yeah. So the resulting theory will be 5-dimensional, compactified on a circle, and this circle is this one. So here I will have a couple system of 5D plus 3D gauge theory. Well, there are some examples, like if I draw something like this, I can have junctions like this. So D3s, so now you ask me, how this happens that D3 has a, so this is a stupid picture because D3s, they don't have, they are points in XY plane. Here I draw them as lines. So the story is, the problem is that the story is more complicated. The D3s, if I have, for example, Q1 here, if Q1 is non-trivial, for non-trivial omega background, the position of D3 in XY plane, so XY plane becomes non-commutative. So the position of the D3 brane, it cannot be, the X and Y positions cannot be determined simultaneously. So you can only say that, well, you have a wave function. If you have a wave function in XY plane, it's like PQ plane in mechanics, right? You cannot put a boundary condition on wave function that its momentum is fixed and its coordinate is fixed. The same story here. So you have to put conditions either on X or on Y. So this is the D3 brane where I say that it's at a definite X position. So this line here, the dashed line, means that I have a wave function with definite X coordinates for the D3 brane. So that's how it works. And this corresponds to a U1 gauge theory with 2 hypermultiplets. So the 3D theory like this. U1 plus 2 multiplets. Why? Because I have here, so this U1 corresponds to a single brane here, and these 2 correspond to 2 infinite branes here, infinitely long, half-infinite branes here. So this is the story of junctions.
And you also have to take vacuum matrix elements over all lines.
Sorry?
You also have to take vacuum matrix elements over all external lines.
To get a partition function, I have to put vacuum everywhere. To evaluate the partition function eventually, I will need to put the vacuum states everywhere.
And also on those.
Yes. So here, but there is no vacuum there. It's not the highest weight representation, but you can put some W1 and W2 like, okay, it's a representation on functions, so I put delta of w over w1, delta of w over w2 here. These are particular functions on which I connect, and that will correspond to the masses. So m12 is equal to okay, q1 power m12 is equal to w1 w2. So this will determine the masses of this hypermatrix here.
And to get 5-dimensional plus 3-dimensional gauge theory, you also need some non-trivial configuration for the 5 branes.
I should somehow marry these two pieces. I should put something like this here, or I should do something like this. Well, stuff. So this will correspond to some bound. So for now, if I don't draw this left piece and right piece, it's going to be a trivial 5-dimensional theory. And if I draw them, then it's going to be a coupled system.
A coupled system from 5-dimensional point of view is some theory with defect or what?
Something like this, yes. Yes, it's a defect which sits in, if you have here Q1, it sits in the Q1 plane, so this one is going to be Q1, Q2. So here, to have a junction, I need to have Q1, Q2 in 5 planes. So there will be a defect along one of the C planes, C2 planes. So that's the defect, the theory with the defect. Okay, so let me.
And it is possible to compute partition function of this theory with defect in an independent way and compare.
Yes, apparently yes. Apparently yes. So I didn't try many examples, but I think it gives the right answer. Okay, now to the final part. Let me see if I do have any time. Okay, good. I have some time. Now I have these partition functions, and I can. They correspond to intertwiners. Now I can ask the following. I can ask if I have a brain crossing. So imagine I have a D5 brain like this, and I have an NS5 brain like this. Currently it doesn't matter if it's Q1, Q2 or Q2, Q3. But the important point is that I now want to draw this picture three-dimensionally. So I have X and Y here, but I also have this tau direction. So these are separated in the tau direction. So if I try to draw it three-dimensionally, it is something like this. No, I don't know how to do it. They are in different planes in the tau direction. And the question is, this also should be some intertwining operator which takes a pair of Fock spaces and spits out a pair of Fock spaces. But then the question is what this sort of operator might be. So I have the two incoming lines and two outgoing lines, like in the junction here. But it should be some special operator.
And this is not junction.
This is not a junction, right?
How is it called?
I call it a brain crossing. I don't know. There is no standardized notation.
Brain crossing is when they move somehow in tau.
Yes.
At a certain moment they cross each other.
No. In tau, I have so this plane sits at tau 1, and this plane sits at tau 2.
I see. And so something happens at tau 1 equals to tau 2, or what?
Yes, absolutely. And yes, this is obviously a special point where tau 1 is equal to tau 2. Let's ask, like, what the separator might be, because these branes don't touch. There is no junction. There is no naively there is no interaction. So what? So the separator from F tensor F. Let me.
So you have two. The branes are 6 dimensional. Yes.
Right.
So you have two 6-dimensional planes. 10-dimensional something. They do not intersect.
So how does this work? Suppose they are this one and this one.
Yes.
So they coincide in Q1 and Q2, CQ1, CQ2. In CQ3 they also coincide, they sit at the origin. And then they are perpendicular in this xy plane, but they sit at different points here, tau 1 and tau 2. And they coincide also in this S1.
So they do not intersect.
So you can forget about all dimensions about x, y, and tau, and so generally it's like this, but at tau 1 equals to tau 2 they cross.
Yes.
As I understand.
Yes. So So the crossing I mean is that I want to draw it like in crossings in Черна-Саймонsa theory. Usually you project on a plane, a three-dimensional picture on a plane, and if you project it on an xy plane, you see that the branes seemingly cross. But in fact, they of course pass one behind another, or vice versa.
At generic values of tau.
Yes.
But in one particular they cross.
They do. I would say they join. Anyway, the terminology is probably bad. So they cross in the crossing is in the projection. That's what I mean. The operator I'm talking about.
I said that if it is like that, then at coinciding time they really cross.
They do really cross, but I call the operator like if they don't really cross, but only in the projection, I call it crossing nevertheless. That's probably bad notation, but still. So we have an operator. We are going to have an operator which I call X, crossing operator. A crossing operator between this. A pair of Fock spaces and into another pair of Fock spaces. What it can be? If they don't interact.
What does this Fock spaces?
So let's
suppose that 0, 1, 0, 0, 1 on both sides. But I mean, the others is the same, or is it meant space to itself, or they have different evaluation parameters?
They have slightly different evaluation parameters, but we will see a bit later.
And this will be seen from geometry.
I think it can be, it might be seen from the geometry, but I will arrive in a different way. It's kind of a little bit of guesswork, but still I think it can be justified. So I have this crossing, and naively, unless tau 1 is equal to tau 2, this should be just an identity, or something like that, a trivial thing. But the problem is that, the important point about all these junctions and crossings is that they are not, you don't write this operator just from your head. It's an intertwining operator, and it's essentially unique. Because it should satisfy the intertwining relations, and this of course constrain the operator almost completely, up to a factor, I guess.
And from today's theory, tau 1 to tau 2, what does it mean? Evaluation parameters are equal?
No, we will come to this. So this tau plane is completely different from this story about evaluation parameters. Evaluation parameters, they sit in xy. So the positions in xy.
I see. So x depends on this parameter tau, and some values of tau is related.
Yes. No. So this naively. So the right answer is that naively, and this is true if Q1 if Q3 is equal to 1 as a degenerate point. So if in the conventional case, if T is equal to Q, there is actually this is an intertwining operator.
Yeah, it satisfies all axioms. Yeah.
Yes.
Very good solution.
Absolutely perfect. Until we want to go to Q3 not equal to 1. In which case, the identity is not an intertwining operator. But one can...
Why?
This just happens so.
No, you didn't explain between words and words. So
Yes.
you can substitute parameters such as it will be defined, right?
Right.
Yeah.
Of course you're right.
Something more clear.
Yes, of course you're right. Yes. So you have to do something. So let us try to go to this point tau 1. So for Q3 non-trivial, let us go to this tau 1 equal tau 2 special point where they really cross. There is really a crossing. And when I really have a crossing, I can argue that this can be, so this picture for tau 1 is equal to tau 2 is really a crossing. And then I can argue that this can be deformed. Now it's a bit like this geometric transition. So this can be deformed into this picture on the top right blackboard. And in this picture I have another parameter, this parameter, deformation parameter here. This is the, well, more or less the length of this segment, which I denote by Q. So that's the ratio of U, V and V prime. So Q is something like a V over V prime or vice versa, I don't remember.
You totally confused me because you just said that V or U somehow related with position in X and Y plane.
Yes, so V.
But now you coincide. So
I go from this to this and then split them in this direction.
And split in time direction.
This one is in time
No,
direction.
not in time, in space direction.
Yes, that's what I do. So I go from this sort of deformation, I go here and then they merge and I split them in this thing. So it's a bit like the geometric transition.
And what is the statement? This separated given by this picture is equal to your X
for particular values of Q.
for each.
So the particular values of Q are Q3 plus minus 1/2. So there are special values of this. So this is an intertwining operator by construction. And I have here, so this U and U prime and V and V prime are related. And I have some special values of Q at which the operator simplifies. You know that there are this special values. Well, how does it simplify? For example, it starts to annihilate the highest weight state. Right? Something like if I put highest weight state here, in general, it gives something. But if Q is a particular value, then it gives highest weight state back. Another so why this is special? And so the conjecture is.
But how do you know? For example, if you look at the left picture,
yes.
How do you know that it should kill some highest weight states or do something like that?
I don't. So the argument here in favor of this Q plus minus is the following: that if I have this three-dimensional crossing, and I suppose I have not 2 but 3 branes, the third one going somewhere here, I will have 2 more crossings. I don't know, like this, for example. And this should satisfy Yang-Baxter equation. Right? So these operators should really satisfy Yang-Baxter equations. And so they should be really R-matrices acting on representations of this algebra. In this case, the Fock representations of different slopes. And it turns out that if I deform it like this and put Q plus minus to these values, this really will give me the R-matrix, the true R-matrix of the theorem, which I know because the universal R-matrix is actually known for this algebra. So for this, it's this crossing. So how do I call it? This is the crossing, and this is the deformed crossing XD. So for this XD of Q plus minus is equal to R plus minus 1. Evaluated, of course, in the F tensor F 1001. This can be checked.
X D. What is
Deformed. The deformed. This D is, I don't know how to call it. This the deformed XD of Q. It will depend on the deformation parameter Q. Well, there will be two special values of Q for which it satisfies the Yang-Baxter equation, for which it is really R-matrix.
I don't know, what is the definition of XD of Q?
XD of Q is a combination of intertwining.
This is just product of two
Yes.
a first operators.
Yes.
For any Q, and where tau?
Tau is not here because another leap of faith. So the idea is that the theory is does not really depend on tau 2 minus tau 1. It depends on tau 2 minus tau 1 in a piecewise constant manner. So the crossing operator, okay, x depends on tau 1 is a piecewise constant.
Okay.
So tau 1 and tau 2, they don't enter manifestly. They enter only the sign is important.
Okay.
So the sign of tau 1 minus tau 2 corresponds to this sign plus minus. So I have either over or under crossing. This corresponds to R, either R or R inverse.
XD of Q, is it depends on Q or Q should be very special? Plus or Q minus?
XD depends on Q, but then there is the claim that this XD for special values of Q is really X. So I have, so now I've drawn one X.
It's a bit strange logic because you say that it's proportional to sign, and at the point where sign is not defined, at tau 1 equals to tau 2, you replace it by some XD.
Yes.
And then you say that these two versions of this XD, they correspond to either plus sign or minus sign, yeah?
Yes, this is the kind of twisted logic, but
It's like you go with a sign, and this is one limit, and this is another limit.
yeah. So let me draw it. I have this tau 2 minus tau 1, which you can call delta tau, and then there is a function which is here, and then there is this Q, and Q is so this Q branch, it starts only when delta tau is equal to 0, right? So the claim is that the picture is like this. So I have this Q is actually a plane, right? Q is a complex number. There are two special points in this plane, Q plus and Q minus. And my function is really a function of Q, but when it approaches these points, then another branch of vacuum goes from these points. So classically, in the degenerate case, Q3 is equal to 1, these 2 points merge. Moreover, the operator is trivial. And then I can go in whatever direction I want. But when Q3 is non-trivial, I can, from one point, I can only go in this direction, and from this point, I can only go in that direction. So that's the idea. That's really a very, it's not just reminiscent of the geometric transition. It is the geometric transition. So if you look at it from the point of view of topological string, refined topological string, so the refinement is like this: that you have two branches. There is in a refined case, which is this non-trivial Q3, you have two branches in two directions. So this is the Higgs branch. You can call it the Higgs branch. It is separated into two pieces, and they join at two different points of the Coulomb branch. So this is this is sort of a little bit. It requires some guesswork.
But so then you say that x plus minus is basically equal to r plus minus 1, yeah?
Yes.
And this is the exact answer.
Yes.
But you also have to specify something or not. Your Fock spaces are.
Yeah, the Fock spaces are, for example, Q1, Q2, Q1, Q2.
And what about U and V?
You have U and V. Any. So you can have a crossing. The crossing. So U and V, they specify where these two are located. So for now,
it's just independent.
Yeah,
because
it's more or less independent of U and V. This particular operator.
Just to go to U and V, because again, so you have U and V, you have to prime and prime, and more or less you prime is U times some Q.
So Q3 this one.
But matrix should map space to itself?
No, because there is a piece with central charge. There is a piece with a grading, so how does this work? So that's a good question, because I have an answer for it. So there is a piece in the matrix. Okay, nice. I continue here. Okay. Yeah.
It has shifts and the code shifts in relation to R.
Yes. So and if you see times something, and this if you evaluate this shifts, then it is exactly like this.
What is there? CD?
Okay, so C is the exponent of C1 is gamma, and there is the same piece with C2. The exponent of C2 is gamma orthogonal, and the D1, D2 are grading. So D1, D2 acting on, so this D1, D2 can take an element P and M of the algebra, and this is going to be NM times P and M. Might be a bad way to write it. It's either N or M, and here it's either D1 or D2. It's just grading operators. So they, in the language of false spaces, they shift spectral parameter. That's what they do.
But now this is just a definition of, I mean, if we know there is an universal matrix, we know this. Yes, somebody proved it, and we know how it shifts relation. We can compute how it shifts relation parameters, and this is easy. But I would say that's a definition. More
or less, yes. So
what can be checked?
Yes.
I'm sure you check something.
Yes. There is one can do different checks. So first of all, one can check if this, if all this strange stuff satisfies Yang-Baxter. So it does. In general, it's interesting that XD of Q, it also satisfies Yang-Baxter-like equation, but with some coefficient. It's sort of an anomalous Yang-Baxter equation. It satisfies up to multiplication by a constant. But at this particular value, the constant is trivial, so it does satisfy the Yang-Baxter. What do I mean by this? I have two of these crossings, and then I know that here I can put an R-matrix onto parallel legs. And I ask if this is equal to this R, and here is something like U1, U2, U2, U1, something like this.
But what are these crossings?
These are X.
How this picture is related to picture when you diverse in time. Not related at all.
Okay, you can say that you cannot. Okay, what would be a stronger check if I had an equation like this, but there is a particular limit where the legs are parallel. The legs are parallel, and still there is a non-trivial relation here.
I think we should stop and check if anyone is alive in Zoom.
Oh, we're going to check this.
Someone.
Is Кто там жив?
Я Рома.
Рома? Отлично. А чего вы молчите тогда?
Даже сказать нечего.
No, just my proposal, if we can claim that the seminar is over, and we can then ask Егор.
Maybe Егor wants to make some conclusion, maybe not.
Yes, I can give just a very short summary. So there is this dictionary, but the new part is that the idea is that whatever you draw with this brains can be translated into representations. And the question I tried to answer is what happens if I have this how do you call it, like skew lines, the lines which pass one behind another, and the answer is that it's very plausible that they correspond to an R-matrix. This brain crossing corresponds to an R-matrix of the algebra. So this
for whole spaces with different slopes.
yes, with different slopes, and so this would make it, the theory very similar to Черна-Саймонsa's theory, which also lives in a 3D space. But then there are more brains in this case. There are just Wilson lines, but here there are many brains. You can see here there can be indices Q1, Q2, but they can be in principle differ. These two brains can be of different types. In which case there are interesting identities, like this Hanani-Witten identity, which relates R plus and R inverse.
But you can't draw this picture with a different
No, this one we cannot draw. But then there is this conjecture that this definition still works.
Is Hanani-Witten relation is it not known for these R-matrices?
I'm not sure. I think not.
Can you write it down?
Yes, I can draw it, and I can of course it corresponds to a relation, but like the relation which can be checked easily. So there is a.
Кроме Ромы там все вымерли. Yeah, I think we should stop here.
Yeah. Okay. So that was the summary, and then let's stop.
Thank you, Егор.
Thank you.
Yes, maybe I want to ask a question.
My suggestion, if Rutau is not asking any questions, then switch back.
But I think so. Like,
Roma, would you like to continue to be present at the discussion? Or you want to ask a question and then go home?
Well, maybe actually I'm a bit tired. Maybe I would go.
Okay, then please ask the question.
Okay. So, what is precise meaning of this vacuum space, like with this plane and two branches out of it?
This
like,
one.
I mean,
This one.
Yeah.
It's just the parameter space of this crossing. So I want to denote it like how can I deform this picture? I can deform it if tau 1 is not equal to tau 2, then I'm free to move in this tau 1, tau 2 direction, here or there.
No, but right? Can it be like some? Oh, so there's no like representation theoretic statement, right?
No.
Actually, representation does not depend on tau.
I think not. So yeah, there is no dependence of the operator here on this line and on that line. That's the claim.
So the interquiner is just R-matrix.
Yes, at this point. So here is x plus equal to R, here is x minus equal to R inverse.
And you claim
Let's thank the speaker again.
Thank you.
Let's cut the провода. How to say?
Можно еще один вопрос задам?